Welcome to 10.9/10.10. We're looking at applications of Taylor and Maclaurin series. All right, so one application is in integration, right? So if we have something like this, right, x cubed to and times e to the negative x cubed, there is no really nice integration technique that we can use to integrate this expression directly. So what we're going to do is we're going to rewrite what we have over here as a power series. And then we're going to integrate that power series and figure out the coefficient on x to the 10th power. All right. So this is one application. Let's go ahead and try to see what we can do here. All right, so first, x cubed. Well, x cubed itself is a polynomial, right? So there's no really, not really a power series representation for that. It's just x cubed. So we need to worry about e to the negative x to the third power, right? We want a power series for this. Right. So let's start with a simple one, e to the x. Right, e to the x is one of the nice one that we know, and it looks like this: 1 plus x squared over 2 factorial plus x to the third power over 3 factorial plus dot 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 x to the n over n factorial. All right. All right. So now to find e to the negative x to the third power, all we need to do is replace all the x's in the power series representation of e to the x with negative x cubed. Right, so this will look like 1 plus negative x to the third power plus negative x to the third power over 2 factorial plus negative x to the third power over 3 factorial. Oops, messed up a little bit. So x to the negative cube square over 2 factorial plus negative x cubed to the third power over 3 factorial. All right, and the general form will look like negative x to the third power to the n over n factorial. All right, so let's just write out the first few terms and see what we have. All right, so that's 1 minus x cubed plus x to the 6 over 2 factorial. I'm going to keep the denominator as factorial minus x to the 9th over 3 factorial and so on. Okay. All right, next. Now we have the power series representation for e to the negative x cubed. All we need to do now is just multiply x cubed to it, right? To get the expression that we have here. All right, so x cubed times this thing, 1 minus x cubed plus x to the 6 over 2 factorial minus x to the 9th over 3 factorial plus dot 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 dot. All right, and let's distribute that x cubed in there. I get x cubed minus x to the 6 plus x to the 9th over 2 factorial minus x to the 12 over 3 factorial and so on. Okay, so integrating the original expression that we have is the same as integrating the power series, right? Which is easy to do because they are just polynomials, right? All right, and so on, dx. Okay, so notice that the question is asking us to find the coefficient on x to the power of 10 after integration. So really, we just need to focus on the terms that will give us x to the power of 10. Right, but for the sake of this example, let's just integrate the first 4 terms. Right, so we have x to the 4th over 10 minus x to the 7 over 7 plus x to the 10th over 10 times 2 factorial minus x to the 13 over 13 times 3 factorial plus dot 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 dot. All right, so the term that we are interested in is this one, right? X to the power of 10. that is x to the power of 10 over 10 times 2 factorial, that's 20, right? So here we can say that the coefficient of x to the 10 is equal to 1 over 20. Okay, and we're done. All right, let's look at our next example. Another thing we can do with power series is to evaluate a limit, right? So if you just evaluate a limit by plugging everything in, we get 0 over 0. Now, of course, you can do L'Hopital's rule and stuff like that, right? But you can see, probably you can see that in this case, it's going to be a little crazy. You might need to take L'Hopital's rule a couple of times. So for the sake of this example, let's since we're in this section, let's just try to use power series to see what we have. All right. So we can represent sine x as a power series. Now notice that the minus x plus x cubed over 6, they are already polynomial, and in the denominator we have x to the fifth, which is also a polynomial. So really all we need to worry about is the sine x as a power series representation. All right, so sine, right? Now you don't have to memorize this. You can always refer back to the notes. So sine is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus dot, 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 right? Sine is the odd function, so we only have odd powers of x's, all right? And then minus x plus x cubed over 6, everything over x to the fifth power. All right, so by looking at the numerator, there are things we can cross out. For example, the x minus x, right? And the negative x cubed over 3 factorial. Now, 3 factorial is actually 6, right? So we can actually cross this out. That's negative, and that's positive, right? And let's see what we have left in the numerator. All right, so we have x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus dot, 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 dot. Right? And everything over x to the fifth power. All right, so let's clean this up a little bit. I'm going to rewrite it by putting this x to the 5 in the denominator to every denominator in the numerator. Right. Now that might not make sense what I said earlier, but so I'm going to put it like this: x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus x to the ninth over 9 factorial and dot, 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 dot. Okay, and I'm going to put x to the fifth power in all the denominator, like that. Okay, all right, and let's see what we have. We can cross out the x to the fifth, right, here in the first term. And here I have x squared left. In the third term, I have x to the fourth left. All right, so really at the end, what we have is this. Limit x to 0, 1 over 5 factorial minus x squared over 7 factorial plus x to the fourth over 9 factorial. And if you want what the next term is, it's going to be minus x to the sixth over 11 factorial, and so on, right? So besides the first term, all the terms after the first term, they are going to have x's in the numerator. That means when we take limit as x approaching 0, all these terms after first term, that's going to go to 0, right? That's 0, and that's 0. Right? So the limit actually goes to 1 over 5 factorial, being that it's the only constant term, which is 1 over 120. Okay, and that's it. All right, another common example of power series is that we can use that to find the sum of the series, right? So for example, here we have infinite sum of pi to the power of n over n factorial. Okay, so let's be a little careful here, and let's actually do a quick review on e to the x, right? E to the x, a power series looks like this, right? X to the power of n over n factorial, which is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 dot. So notice that this actually has the same resemblance as the power series of e to the x. But instead of having x's in here, right, we have pi's in places of the x, right? So one could say that this is actually just e to the x, but with x replaced with pi, right? So that's one other technique that we can use to use the power series to find the sum of a specific series, right? Let's look at a couple more examples. All right, so this is the second one. Now, unlike the first one, it's actually not that obvious of what this looks like, but we do see the 2, 1 plus 1, 2, 1 plus 1 factorial, and then the -1 to the n. That sort of looks like some type of trig function, right? Not going to spoil the fun, but let's write out the first few terms, right? So that's going to be pi over 2 plus pi cubed over 3 factorial times 8. Oh, sorry, it's a minus, and then plus pi to the 5th power over 5 factorial times 32 minus pi to the 7 over 7 factorial times 128, and so on, right? Okay, so what I'm going to do now is I'm going to look into each factor and then factor out pi over 2. All right, so first one is just going to be pi over 2 minus, that's going to be pi over 2 to the 3rd power over 3 factorial, right? Now denominator 2 to the 3rd power is 8, and that is from the denominator here, right? So the denominator 8 is now in here. Right. So we're going to do the same thing for the rest of them, right? Plus pi over 2 to the 5th power over 5 factorial minus pi over 2 to the 7th power over 7 factorial plus dot, 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 dot. Right? And then you can actually tell that pi and 2 are having the same power by looking at this factor right here, right? They both have power of 2, 1 plus 1. Now, hopefully you can see what trig function we're looking at, right? If not, let's do that. So notice how we have pi over 2 in all the places. Now let's replace that with x, right? Let's see what we have. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus minus x to 7 over 7 factorial plus dot, 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 dot. Right? That's an odd polynomial, right? And which trig function is odd? That's right. It's sine x, right? So sine x is has the power series representation of the above. So what we have here is actually replacing x with pi over 2, right? So what we're looking at is actually just sine of pi over 2, which is 1, right? Pretty interesting, right? All right, next let's look at a few more. All right, now let's look at this one. Now, this one is also not that obvious, but again, let's first just write out the first few terms, see if we can get an idea. So we will have 1 minus 1/3 plus 1/5 minus 1 over 7 plus dot, 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 dot. Right, so just by looking at this, it's pretty hard to tell what we have here, right? So let's try to come up the general form that we have here, so we can look into some of the common power series that we talked about and see if this has some resemblance of what we have, right? And the one we have is this. I'm gonna write down the power series first, and then I'll show you the function. -1 to the n, x to the power of 2n plus 1 over 2n plus 1. All right, so that looks like this power series looks like this, right? Except we don't have the x. to the power of 2n plus 1, right? So another way to say this is if x is 1, if we pick x to be 1, then we will have the series in pink, right? So this is actually arctangent of x, right? But here, it's actually arctangent of x when x is equal to 1, right? So what we have here is actually just arctangent of 1. And what is arctangent of 1, right? That's right. It's pi over 4. So now things are getting very interesting, okay? We are adding up a bunch of numbers and subtracting a bunch of numbers, and it's equal to pi over 4. So let's write out this equation. And I'm going to write out a few more terms. So 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1 over 11 plus 1 over 13 minus 1 over 15. So hopefully you guys can see the pattern here. It's actually not too bad. And then infinite sum, it's equal to pi over 4. That means when we multiply 4 to the left-hand side, right? When we multiply 4 and this whole thing, that's equal to pi. Okay, multiply 4 and to the whole thing on the left-hand side, that is an approximation of pi. So what we can say here is pi is equal to 4 minus 4/3 plus 4/5 minus 4 over 7 plus 4 over 9 minus 4 over 11 and so on, right? And then of course you can punch that into like a program on a computer and then make it adding like 10,000 terms, and then you can get very close to pi. And actually I actually tried this before. So if I add the first 50 terms of this, I get 3.121594653. Right. So I would say pretty nice approximation for just 50 terms. Now, of course, if you have 100 terms, 200 terms, we will be even more accurate to pi, right? Then pi was around what, 3.1415 and so on. Okay. So another nice way to approximate pi, right? Because pi is a number that we've been struggling with on how do we get a pattern for it, right? Does it have a pattern? What type of number is it? Right. So this is another way that we can approximate pi, is by a power series of arctangent. All right, now here's another example. Um, So it says find the first three non-zero terms of the Maclaurin series for f of x equal to e to the x times ln of 1 minus x by multiplying the two series. All right. So I have put the two series here for you. Now basically all we're doing is just multiply the two polynomials together. All right. So let's go ahead and do that. All right. So e to the x times ln 1 minus x will be equal to that. All right. So the first one is e to the x. The second one is ln of 1 minus x. All right. So I'm going to use different color to represent the distribution. Right. So first I'm going to start with 1 multiplied to just the first three terms. Since we're only looking for three terms, I think multiplying the three terms will be enough. All right. And the second one, let's do green. All right. X times negative x times negative x squared over 2 times negative x cubed over 3. All right, and last but not least, you have x squared multiplied by that, square multiplied by that, x squared multiplied by that. All right, I'm going to write them out vertically and see what we have. Okay, so in blue, we have negative x minus x squared over 2 minus x cubed over 3. Now in green, I have negative x squared, negative x cubed over 2. Now I don't need to multiply the last term because it's gonna be a more than 3 terms, but we can still write it out. That'll be minus x to the 4 over 3. Right, and the last one, x squared over 2 factorial times negative x. That will be negative x cubed over 2. And then let's do one more. That'll be what? Minus x to the 4th over 4. Right, but since we are only worrying about the first 3 terms, right, we can conclude here. All right, e to the x times ln of 1 minus x will be equal to negative x, right, for the x to the first power, and x to the second power we have minus 1/2 and minus 1, so minus 3 over 2 x squared, and then the third power minus 1/3 minus 1/2 minus 1/2, that will be that's minus 1 negative 3, so negative 4 over 3 x to the third power, and then of course the rest of them, right? Since the question only asks us for the first 3 terms, here we go. Now let's look at a radius of convergence and interval of convergence. Now notice that for e to the x, it's very nice. It's actually converging in, everywhere, right? But for ln of 1 minus x, it has a strict radius of 1, and the interval notation is between -1 and 1. So when we multiply these two together, the interval of convergence and radius of convergence will be ROC and IOC will overlap, will be the overlap between the 2 intervals. Right? Or the intersection of these 2 intervals. Now, since the first one for e to the x is everywhere, right? The intersection between these two will just be the same thing as ln of 1 minus x, which is r equal to 1, and the interval will be absolute value of x less than 1. Okay. All right, so in the last part here, I have included another very interesting example, pretty time consuming. So we can just take a look at this. So basically, we want to find the first 3 non-zero terms for the Maclaurin series of tangent. And we know tangent is sine over cosine, and we do have Maclaurin series for sine and cosine, which they are all polynomials. And specifically, the degree of sine is more than the degree of cosine. Now, of course, with infinite power, it's not going to matter too much. All right, and then we can go ahead and do long division, and then we'll get the resulting polynomial, which is going to be the power series or the Maclaurin series for tangent. Right, just something interesting to look at. All right, and that'll be it for 10.9 and 10.10. We are just looking at some applications of Taylor and Maclaurin series. And thank you guys very much.